Hi, my name is Emma O'Neill, and today I will be talking about the clogging of gravity-driven spheres in the presence of shape anisotropic particles, with support from my faculty advisor, Dr. Shubha Tewari. Under the effect of gravity in a hopper, granular particles, although solid themselves, can flow similarly to a liquid. However, this flow is distinctly different than the way that water would flow or any other liquid. For example, when water flows out of a hopper, the flow rate is affected by the pressure of the water above it. The flow slows down as the water above decreases. In granular flow, the rate of flow is constant and the pressure is distributed outwards towards the side of the hopper. In the picture of the silo, you can see an instance in where this has gone wrong. Many applications of this phenomenon include the processing of grains in granular materials, such as pills or gravel. These simulations are carried out using lamps. The particles of the simulation consist of two different sized spheres along with the shape anisotropic dimer. The rate at which particles flow is controlled solely by the opening size of the hopper in comparison to the size of the particles. Along with the percentage of dimers, the opening size of the hopper plays an important role in the probability of developing a clog. For example, a larger opening would be harder to clog. This simulation is also quasi-2D, as the z direction is only large enough for one particle. In the earlier rendition of the simulation, particles permanently leave the system, which creates a max time for the simulation to run. Runs have also been done with a 60-degree hopper angle, but changing the angle does seem to change results, although this finding is very much still in progress, so it is something to investigate further. To go into a bit more detail about the shape anisotropic particles, we are using dimers, which are composed of three 1.2 diameter spheres that have been combined to create a full length of 2.4. We have gone this route as opposed to using an ellipsoid because we want to make sure that every particle in the system will interact the same way with every other one. So by making all of the particles consist of spheres, we can ensure all the interactions will be the same. And the reason why these dimers are so important is because their possible orientation could make clogging either much more difficult or they could act as obstructions and make clogging in systems easier. The results from the original simulation are courtesy of Faisal Siddiqui, whose research I am building off of. From many different experiments, it is known that the distribution of clogging times for flow of grains in a hopper is exponential. We wish to test if this remains true as the concentration of dimer particles increases. We also want to know if the shape of the clogging distribution depends on the opening size. For sizes that are either too small or too large, such as 4.0 and 8.0, clogging occurs intermittently. At openings that are too small, hoppers may clog right away, and at openings that are too big, hoppers will never clog. We wish to investigate more in the intermediate regime, such as the 5.2 opening. In order to improve the efficiency of the simulation, we have made a couple of procedure changes. Firstly, we have made the y dimension periodic. So when you see these particles leave the hopper and the simulation region, they are reintroduced back at the top. Theoretically, this could allow a run to go on as long as needed until it clogs. This is especially important for systems with larger openings and low dimer concentrations, as the longer clogging times will help fill out the data of the tail. We are also making some changes to how we are defining when a system is clogged. The original method tracked the flow rate out of the hopper, and when the flow rate would reach zero for a determined number of time steps, the system was determined to be clogged. However, the new method will track the velocity at different y levels in the hopper region. In an initially clogged system where a clogged arch has already formed, particles above the arch do not move when the simulation is run. However, there still may be a couple of particles that flow out. In the video, you can see that as the system begins to clog, particles will begin to stop. So how did the new simulation change results? The new data is on the left and the earlier data is on the right, courtesy of FISA. The time steps are computed slightly differently since there is an initial time step in the new simulation. However, these graphs are still comparable. As you can see, the new data does take the form of an exponential, while not as steep as the earlier graphs. In the new data, less runs were completed, so the tail has not been completely filled out. Also, by looking at the log Y version, both on the bottom, you can see that the clogging time distribution is distinctly linear, which shows that it is indeed an exponential. Another thing to point out is in FIS's data on the right, the red circles show a 0 dimer concentration. On the left, that is shown in a blue circle. While it stands out very much on the right, on the left, it seems to stand out just a little, but overall takes a similar shape of the other dimer concentrations. These are preliminary conclusions since the investigation is still a work in progress, but we can still make some general observations. First of all, the clogging time distribution are indeed exponential, which matches what is reported in literature and in previous findings. Additionally, we can look at a graph of average clogging times, as seen below, and see that the distribution again is exponential. For larger dimer concentrations, the system tends to clog at a shorter time, while for smaller dimer concentrations, the distribution is broader and the system takes a longer time to clog on average. Since this research is still a work in progress, there are many more things that we can investigate. First of all, we can focus more on the intermediate regime and complete runs for opening sizes 5.0, 6.0, and 6.5 to flesh out that area. Also, we can test how the hopper angle changes the clogging times. And lastly, since granular media tend to segregate when poured, instead of pouring the particles in the hopper, we can randomly generate them in the hopper area and theoretically allow for a more even distribution. Thank you so much for your time today, and thank you so much for watching.